Okay, we're going to get to our last example here in section 4.4, which will be the end of your examples for week 4. First thing though is I'm going to quickly go over the theorem called the second derivative test. So we had the first derivative test, which told us whether a function was increasing or decreasing to a critical point, which told us whether we had a local maximum or a minimum or neither. The second derivative test is similar, except that now we're looking at comparing the second derivative with the first derivative. So if the first derivative is 0, we know we have a horizontal tangent line. If the second derivative is negative, that means we have concave down. So horizontal tangent line with concave down means we have a local maximum. First derivative being 0, second derivative being positive, that means we have a horizontal tangent line, but the second derivative being positive means we have concave up. So concave up with a horizontal tangent line means that we have a local minimum. If they're both 0, then you can't use this second derivative test. Functions at x equals c could be a local maximum or neither. So that's the second derivative test. And then the procedure for graphing a function. Okay, if you want to graph a function, first of all, you want to identify the domain of it and any symmetries the curve may have. Find the derivatives y and y double prime. Find the critical points of the function, which is where the first derivative is equal to 0 or is undefined. And identify the function's behavior at each one, what is going on there. Find the curve, find where the curve is increasing is where it is decreasing, so intervals of where the first derivative is positive or negative. Find the points of inflection, which are where the second derivative is equal to 0 or doesn't exist, and determine the concavity of the curve. Identify any asymptotes that may exist from our stuff we learned in section 2.6, and then plot some key points such as the intercepts and points found in these steps above, just to help you get a good idea of the sketch of the graph. Okay? So let's go through and do an example with that stuff. So let's say we wanted to sketch a graph of the function f of x equals x to the fourth minus 4x cubed plus 10. First thing I want to do is see if there's any symmetry. Symmetry about either the y-axis or the origin. So remember, you want to plug in minus x. So if I plug in minus x, I want to look at f of minus x. If f of minus x happened to be the same thing as f of x, this should say f of x, not f of minus x, okay? Happened to be the same thing as f of x, then you would have symmetry about the y-axis. That would be an even function. If f of minus x came out to be minus f of x, you would have symmetry about the origin, or an odd function. That doesn't happen in either case here, so there's no symmetry to this function. So the next thing I want to do is take the two derivatives. I take the first derivative and the second derivative. Those are pretty easy in this case. Then the next thing I want to do is look at where the first derivative is 0 or doesn't exist. Simple first derivative, so there's no place where it doesn't exist. But I set it equal to 0, and I see that x equals 0 and 3 are critical points, which allows me then to determine intervals where the function is decreasing or increasing. So using the first derivative on either side of my critical points, I can see it's decreasing from minus infinity to 0, still decreasing from 0 to 3, and then at 3 it's increasing from 3 to infinity forward. Okay, then I use the second derivative. Take the second derivative and I either see where that's 0 or doesn't exist. Again, it's a simple second derivative, so I factor it here, and I see that it's 0 at x equals 0 and 2. So these are possible inflection points. Now remember, inflection points are where it actually does have a change in concavity, so we don't know until we look at the second derivative. So here we have the second derivative positive from minus infinity to 0. That means we have concave up from minus infinity to 0. And then from 0 to 2, it's now concave down. So we do have a change of concavity at x equals 0. So x equals 0 is an inflection point. And then again, we do have a change of concavity at x equals 2 as well, because it's concave down from 0 to 2. And then from 2 to infinity, the second derivative becomes positive, which tells me concave up. So x equals 2 is also a inflection point. All right. There are no asymptotes for a polynomial, so we don't need to worry about asymptotes for a polynomial. Look at the y-intercept. You find f of 0. You see the y-intercept is 10. Now I'm going to start to plot some of these things. So f of 0 is 10. So I'm going to plot that point. I'm going to look at the x-intercepts. Those are kind of difficult to find. Solving a 4-3 equation equal to 0. There's nothing that really makes it stick out to me, so I'm just going to leave it. I don't know. Too difficult to find. So then I'm going to plot certain values. Okay, I'm going to plot at my two critical points. X equals 0, I know the function's value is 10. We already did that. At x equals 2, the function value is minus 6, right? X equals 2, the function value was minus 6. X equals 3. Now remember, we had concave down, right? We had concave down from 0 to 2, concave down, and then it was concave up from 2 to infinity. At x equals 3, I just wanted to figure out at that other critical point what I had. The value of the function is minus 17, and I know it turns around there, right? That was a critical point, right? X equals 3, yep. So I know it turned back around there. Again, this is all still concave up, though. At x equals minus 1, f of x was 15, and I just got a good feel for what's going on at that point.